Hello and welcome back to this channel. In this video, I'll walk you through the physics side of Combined Science paper 5129 version 12 of October-November 2011. Let's get started. On to question 1. The diagram shows an instrument used in physics. Here's the diagram. What is the name of this instrument and what is it used to measure? Here are the options. Now, we can recognize from the diagram here that this instrument is a micrometer, not a caliper. Caliper will have jaws, something like this. Okay, it's not that exactly accurate, but it's somewhere like this. Whereas this micrometer has this U-shaped frame over here. And to measure, you put something or this item in between this cylinder. We also know that this micrometer is used to measure length. Length, how do we know? It's from this sleeve, the feature sleeve over here, and another feature from here is called thimble. So, first is micrometer. The second one, it is used to measure length. Therefore, the answer is C. Now, on to question 2. In an energy transformation sequence, what produces kinetic energy from gravitational potential energy as part of the sequence? And here are the options. But before we go to the options, let us create a blockchain out of this energy transformation sequence, which is right here. It says right here, from gravitational potential energy, let me write down here, a short form, gravitational potential energy, to kinetic energy, which are presented as Ke. Now we need to match this sequence onto one of the following options right here, A, B, C, D. Let's start with A. A, burning fuel. We know that fuel is chemical energy. Let me write as CE. Chemical energy. When you burn fuel, it'll create heat. The second one is heat energy. This heat energy is used to turn water to steam. So this steam is used to propel the turbine. So the turning of turbine will create or is in the form of kinetic energy, which will then be used to generate electricity. Electrical energy, let me just write it down as EE. So this does not match what we are looking for. A is out. B, generating hydroelectric energy. Now, hydroelectric energy is usually harnessed from water in motion or waterfall or water released from dams, as in this wood, or water reservoir. So in this case, the water needs to be from a high or from a height. Okay, from a height, such as the waterfall. So from a height, this is usually in the form of gravitational potential energy. The water then falls onto the turbine, which will then be used to convert to electricity. The turning of turbine is in the form of kinetic energy, which will be later converted to electrical energy. Option B matches what we are looking for. But for now, let us go through everything just to be sure. Option C, generating energy in nuclear power station. Nuclear power station is similar to the option A, which is burning fuel in power station. But instead of coal or fuel they use in option A, they're using a radioactive source or nuclear source to produce electrical energy in this case. So in this case, it is same also chemical energy to be converted to heat energy, which will then be converted to kinetic energy and later on electrical energy. As C is out. Last but not least is option D, generating energy in geothermal power station. Now, geothermal power station uses the heat emitted from Earth's interior to generate electricity. So the energy conversion goes from heat energy to kinetic energy in the form of turning the turbine, then on to electrical energy, generating electricity in generator. So therefore the answer in this question 2 is B. Now moving on to question 3. Which car moving from rest has an average acceleration of 2.0 meter per second square? Let us recap back what is the formula for acceleration. I shall write it down here. Acceleration is equal to change in velocity divided by change of time or time taken, whichever you prefer. We shall then calculate the acceleration for each of the options with this formula. The initial time and velocity in this case is both 0. So let me expand the formula first. Wait, hold on. Yes, let me expand the formula first. A is equal to V final minus V initial divided by T final minus T initial, or sometimes some school uses V minus U divided by T, which is more simpler, but whichever you prefer. So the initial here, as I mentioned before, U is equal to 0, T initial is equal to 0. Now let's move on to A. The speed is 10 meter per second in 2 seconds. A is equal to V minus U divided by T. We know U is 0. So V is 10 in this case because it reached the speed of 10 meter per second. Minus U equal to 0 divided by 2. So 10 divided by 2 is 5 meter per second square. So that's not what we're looking for, but let us move on. B, a car reaching a speed of 20 meter per second in 5 seconds. Again, the same formula. It's good to rewrite the formula back so that we are aware of what's in there. So V is 20, U is 0, T is 5. 20 divided by 5 is 4 meter per second square. Option C, a car reaching a speed of 30 meter per second in 10 seconds. A equal to V minus U divided by T. V is 30 minus 0 divided by 10. 30 divided by 10 is 3 meter per second square. And on to option D. Let me make a border first because there's no space anymore. A divided by V minus U. A is equal to V minus U divided by T. Sorry about that. V is 40 minus 0 divided by 20. 40 divided by 20 is 2 meter per second square. So this is what we're looking for, as this matches what the question wants. So D is the answer. The car reaching a speed of 40 meter per second in 20 seconds. Alright, on to question number 4. A force is applied to an object on a frictionless surface. It produces an acceleration of 3 meter per second square. What are the possible values for the applied force and for the mass of the object? Here we have 3 variables. The first one is acceleration of 3 meter per second square. Let me rewrite it in the equation form, as in like this. A is equal to 3 meter per second square. Second and third variable in this question is the applied force and the mass. So from these 3 variables, we can form an equation which is F is equal to ma. Now, we have to match. I'll say match one of the options to get acceleration of 3 meter per second square. We can do 2 options here. One, and the easiest or the most straightforward method, is make acceleration, or A, as subject. So in this case, A is equal to F divided by M. When we do this, wait, hold on, let me move this one out first. Okay, there we go. Alright, when we do this, we can then find the acceleration for each of the options right here. Let me do it first. So F should be divided by M. With the use of calculator, for option A, 2 divided by 5 is 0.4 meter per second square. Option B, 2 divided by 6 is 1/3 or 0.333 and so on meter per second square. Option C, 5 divided by 2, which is 2.5 meter per second square. And last but not least, the option D, 6 divided by 2 is 3 meter per second square, which is what we wanted. So the answer is D. This is very straightforward. Alright, this is the first method. The second method is you have to multiply the value A, which is 3 meter per second square, with mass, and match it with the force. If it matched together, then that's great. If it doesn't, then that's not the answer. I'm gonna show you the first one only. So you can try the second one if you like to see whether you get the same answer or not. Let us move on to question number 5. Question number 5. A man pushes a heavy box across a floor. He exerts a force of 18 Newton and the box moves 4 meters in 5 seconds. Let us extract these informations and convert or transform them into equation form. Let me highlight the information first. Force of 18 newtons, moves in 4 meters, and in 5 seconds. So with this 3 information right here, force is 18 Newton, distance is 4 meter, and time is 5 seconds. The question asks the useful power. What useful power does the man develop? So from these 3 variables, we can form an equation, or we can recall the equation that relates to power, which is P is equal to work done divided by time. Work done, we can break down the work done into force times distance divided by time. So we know force is 18 newtons. We know the distance is 4 meters, and we know the time is 5 seconds. With the use of calculator, you'll be able to get the answer. Okay, let me manually write this down first. Okay, 16 times 4 is 64. Powers is in the form of watts, in the units form. So the answer is B, 64 watts. Alright, let us move on to question number 6. Question number 6. At regular intervals along a rail line, there is a gap between the rail sections right over here. What is the reason for the gap between the rail sections? Here are the options. So I'll say in syllabus, by right, they'll explain to you what's the reasoning between the rail sections gap. But for the purpose of this video, I'll go through one by one of these options and explain to you why and why not. Okay, let's move to option A. To allow for expansion of the rail sections during hot weather. This is a possible reason. Let me write down here. Possible because when it is hot or during the hot weather, rail sections, which is made of metal, expand. And when they expand, if they don't have any room or no space, they'll bend. So, to prevent bending, they give gaps for expansion. So this is possible for option A. Option B. To allow vibrations of the rail section as train passes over them. This is not really the reason behind the gap in the rail section. Vibrations, not really so. Yeah, not really so. I won't go into detail on this section, in this option, sorry. Option C, to allow rainwater to drain from the rail section. This is not a strong reason for the existence of the gap, as the rain can still run off from the sides of the rail section. It does not depend on the gaps. So, nope. To keep the wheels of the train and the carriages on the rail section. In my opinion, to keep the wheels of the train and carriages on the rail section, it should be the design. Let me write here. Design of the rail section, not the existence of the gap. So option A matches or is the most possible reason why the existence of the gap is there. Alright, question 7. Which property is essential for or to a clinical thermometer? A. It contains mercury. It contains mercury. Okay. In option A, traditionally, there's two types, mercury and alcohol type of thermometer. But nowadays, thanks to the pandemic, digital infrared thermometers are everywhere. So back to this option, let's pretend that it's still traditional since it's 2011 paper. The distinction between the two types is just the mercury can have larger range as compared to the alcohol, but it's more toxic if the thermometer were to break. So this is not really a strong property, not the most important property to the existence of this clinical thermometer. Not yet. Let's move on to the other options right here. It has a constriction in its bore. Constriction meaning this is the thermometer. This is the bulb. Let's pretend that's the bulb right there. Constriction is this little bump right here. Let me write down this. Constriction. Okay. The function of the constriction is to stop the level of the liquid from falling back into the bulb very quickly or too quickly. This helps the nurse to take down the correct reading of the temperature of the patient. That's just an example. So the feature of having a constriction is very important in this case. Now, let's move on to option C. It has a range of 40 degrees Celsius. In this case, the reduced range, meaning the smaller range, will result in an increase in sensitivity. But before that, let us move on to the last option right here. It is accurate to 0.001 degrees Celsius. This is not actually necessary to get a very precise reading of temperature, as the normal temperature of human body usually range from 35 degree to 40 degrees Celsius. So this also can only be obtained in digital thermometer, not really on clinical thermometer or physical thermometer where you have to physically read the level of the temperature. So the option that is most essential or the most important property is B, the constriction property. Right here. Let us move on to question 8. The diagram shows the reflection of a ray of light from an object in a plane mirror. Which statement is correct? Alright, we shall go one by one through the options right here. A, the image is at X. Okay, image at X means the image is on the surface of the mirror. Whoops, that was highlighted. Okay. Which is not what happened when we see ourselves in the mirror. Usually we see ourselves behind the mirror surface. A is out. B, image is between X and Y. X and Y meaning somewhere here. Image between X and Y means the distance obviously is lesser than the distance between the object and the mirror surface. Okay, this is what it means. The distance between the object and the mirror surface, which is right here and here, should be equivalent to the distance from the mirror to the image behind the mirror. Not less, not more. So in this case, B is out. Option C, the image is at Y. This is what we're looking for because the image is exactly on the exact distance from the mirror surface as the distance between the object and the mirror surface. C is the correct answer. But before we conclude the answer fully, let us move on to option D. The image is between Y and Z, which is right here. As I mentioned previously, this is not possible. It's only here that is possible. Wait, hold on. Let me highlight. There we go. It's only Y is possible. The position Y. D is out. So the only answer is C. Now with that done, let us move on to question 9. Question 9. Wait, hold on. Okay. A VHF. VHF means very high frequency radio station broadcast at a frequency of 60 megahertz, or in bracket 6.0 times 10 to the power of 7 hertz. The speed of a radio wave is 3.0 times 10 to the power of 8 meter per second. What is the wavelength of the waves broadcast by the station? So from this question right here, we can extract out the information such as below or such as in here. Frequency is 60 megahertz. Let me rewrite here. Frequency is equal to 6.0 times 10 to the power of 7 hertz. Speed of the radio, or we shall write it down as V, is 3.0 times 10 to the power of 8 meter per second. The question asked here, what is the wavelength? Whoops. Okay, hold on. What is the wavelength? Wavelength is in the form of lambda. We don't know this, so we need to solve for lambda. Between these three variables, we know that there's one formula that can relate to these three variables, which is V is equal to frequency times lambda. Make lambda as subject because we want to find out what's lambda. Lambda is equal to V divided by F. And we know V is 3.0 times 10 to the power of 8 meter per second divided with frequency. Frequency is 6.0 times 10 to the power of 7 hertz. With the use of calculator, you can calculate that this is equivalent to, hold on, let me calculate myself first. This has become 1, this has become 0.5, but 0.5 times 10 to the power of 1, which is 5.0 meter. Okay, so the answer is 5 meters. So the answer is A. Please use calculator, don't do like me. Alright. Next, let us move on to question 10. Which diagram correctly shows the directions of the electrostatic forces on a pair of charged spheres? Okay, before we move on to the options right here, let us recall what we know for charged sphere or charges. We know that charges, especially like charges, repel. Okay, how do you spell repel? Wait, hold up. And then, unlike charges, attracts. So from here, we can identify or at least know how the behavior of these two spheres should be. Okay, in option A, we have negative and negative. Negative and negative is like charges. Sorry, yes, it is like charges. Oh my god. Like charges meaning there's existence of same charges. Negative and negative. So the arrow points towards each other, which is not supposed to be this way. It's supposed to be away from each other because like charges repel. Okay, let me write here. Repel. Okay, so A is out. Now, B, you have two positive charge sphere. So the direction of the force is in a vertical motion. It is one is up. Hold on, one is up. One is down, which is not supposed to be this way. It is supposed to be in the repel motion, which is like this. Next, this is like charges. No, this is not like charges. This is unlike charges. Oh dear. So unlike charges should attract. Let me write down here. And the motion should be like this, not the opposite. So C is out. Now D. Another unlike charge spheres. And this time, the direction is correct. It is towards each other. The answer is D. Okay. Let us go and move on to the next question. Oh dear, where's the next question? Okay, question 11. Question 11. The diagram shows an unsafe use of an extension cable shown here. I hope none of you have done this. This is very dangerous. As you can see right here. What is the electrical hazard? Let us go through one by one. A. The danger of burning out appliances. Okay. In the question, there's no information about appliances. It has mostly to do with the cables or the plugs, which is too much plugs or too much 3-pin plugs in single extension cable, which is right here, being divided to many appliances. Can see 1, 2, there's maybe 2 right here. Another one, there's 3 pin plugs. No, there's 3 plugs here. And last one is there on the side. Okay, about the appliances. If the question tells us about the appliances, then we can determine whether it is the danger about the appliances. That for now, let's just focus on the cables. So A may or may not be the reason, but for now, not yet. B, the danger of melting the fuse. In this case, we do not know the fuse rating, nor do we know the current the value of the current flowing into this extension cable. So it may be dangerous, but who knows, maybe the fuse rating is low or high. We don't know. In this case, no. Option C, the danger of overheating the cable. Okay, this is the most plausible reason or the most plausible hazard in this scenario. Too much 3-pin plug. Too much plugs on a single extension cable can cause an overheat. C is a possible, but let us be sure and move on to option D. The danger of appliances not being earthed. Okay, normally when we see a 3-pin plug, we can safely assume that there's an earth wire. There are some exceptions, but normally there is an earth wire. But in this case, we shall rule out the option D. So the answer is C. It has to do with overheating the cable. Too much plugs or unsafe use of plugs. Unsafe use of extension cable, sorry. Okay, with that aside, let us move on to question 12. Question 12. A constant voltage source is connected to a resistor which has a current I through it. Two more identical resistors are then added in series with the first. What is the current now? Okay, in order to answer this question, we need to draw two diagrams. First diagrams, I think I need to zoom in. Hold on. The first diagram is before adding the two identical resistors. So in this case, let me use a thinner line. In this case, let's pretend you're using one single cell. Then you have a resistor here. Okay, excuse my bad drawing of circuit, but yeah, that's how you should look like. So we have constant voltage source. That's the main key here. So the voltage is V. Let's pretend the resistor is R. So we know that the current flowing here, okay, that's wrong. The current flowing here is I. Let us use the formula V equal to IR to represent I as V divided by R. Let us draw a second diagram with the two identical resistors, which is right here. Same cell, but just more resistors. Okay, right here, R, V, but we don't know the I. Again, with the same formula, V is equal to IR. We're trying to identify what is I, V divided by R. I know it's the same as the first one, but hold on. We need to figure out what's the total resistance in this second diagram. Total resistance, okay, that's wrong. Total resistance, the second diagram is 3R. How do I know? It's R plus R plus R because of the series arrangement. So in this case, V is divided by 3R. We can then separate this V divided by 3R into a third multiply with V divided by R. We can then substitute this value or this variable or V divided by R variable with the first one, which is right here. So the value will then turn to 1/3 of an I. The answer will result to B. I divided by 3 is the same as this one. So the answer is B. A bit time consuming to figure out, but yeah, it's good to know this. Okay, next, question 13. The transformer in the diagram has an input coil with Ni turns and an output coil with a No turns. Here's the diagram, here's the input side, and here's the output side. The output voltage needs to be lower than the input voltage. Okay, let us write down first before anything else. The output voltage needs to be lower than the input voltage. What is needed for the transformer to work correctly? First of all, for the transformer to work correctly, you need an AC, which is an alternative current, not DC. So the option C and D is out. We can just focus on option A and B. The relative value of Ni and No, we can see there's two signs here, or we can just use this to flip around. So Vi should be more than Vo, and we know that Vi is proportional to Ni and No. So we need to have a greater value of Ni compared to No. So the option A is the answer, as this matches what we wanted. And that's it for this video. I hope everything is clear. I'll see you in the next video.